Okay, so let me record. Okay, so I was discussing this, inductive invariance and over and under approximations thing. See, there is, as I told you, there is a very rich theory behind this thing, and the basis for all that is more logic. Now, we are not foundation because that is as it applies to program, and so that's why I'm doing it in. Can you hear me well? Because the internet is a bit unstable, so you have to let me know by yelling. Okay, when my voice breaks up. Okay, I'll try to speak as close to the microphone as possible. Okay. Anyway, the plan today is I'll take about half an hour to finish up this discussion about why inductive invariants are important and how they are useful in verifying properties of programs. And since DNN can be considered as pretty much you could model it as a program where every layer, the computation that gets performed in each layer can be considered as an assignment, can be modeled as an assignment statement. Okay, therefore the entire thing can be considered as a program as far as its behavior is concerned. So this theory is of inductive invariance gets carried over to neural network verification as well, and that's why I'm covering this without the complete details of the theory, but in a more illustrative, intuitive fashion. But it's important that you understand, and therefore, if you don't understand anything, please ask questions, okay? And since there are some details that I'm glossing over, and if something you don't understand, either because the notation is not clear or the concept is unclear, you will have to let me know. Anyway, so the idea is hopefully I'll finish up in half an hour. Diganta is somewhat late to this class, and I don't think I'll need more than half an hour is what I'm thinking. But after, if there is time left over, which I expect to be, he will start discussing the ACAS network, which is something that we expect you to be using in your final project. And so, we want to get started with that, as I mentioned last time. So he will do that, and he will need more than half a class. Certainly, he'll need one more class. And since we have lost a couple of classes for holidays, so I want for that by converting the tutorial on Thursday into a regular class wherein Diganta will continue to discuss the ACAS network, which is which is a prominent benchmark, DNN benchmark that's used for benchmarking various verification techniques, including over approximation and under approximation. Okay, so that's the plan today. Okay. So, any questions here? So, inductive invariants are, as I said, are predicates. Okay, that characterize at each location, the precise set of values that variables in the program can take at that location in any execution of the program starting from the entry location. Okay, and so that is what is defined as the strongest inductive invariant. As you can see at location L1, this set the set of values that X can take in this case are characterized by this formula. Okay, which basically says X could either be 2, 3, 5, or 9. For the initial value, if you include the initial value 1, the initial value 1 is also included. Okay, in general, you can always characterize the inductive invariant at a particular location in an inductive fashion in this way. Okay, so there is by considering all the incoming arrows to that location, so some of which will be some of which could be looping arrows, and that's why in this case, if you take X prime 2, that is the first time you get to that location. So anything, the initial values included in that, in the set of values that X can take at L2. And if then you define for each of them inductively what can happen based on the action that is the assignment that is made, conditional assignment, possibly conditional assignment for the by that particular edge. Okay, so in this case, the computation corresponding to the self loop can get executed only if X is less than 9. So if you're already in that location, and if X is less than 9, then you should include 2 times X minus 1 as well, because that's the assignment that gets made. Similarly, the values that the incoming arrow X condition on X less than or equal to 2 can produce is, if X is less than or equal to, you can be there as well. But that does not add any new value, and therefore that's why you get this set of values 2, 3, 5, and 9. So I have a question. If one of you could answer, so I'll pick one in the order. Ashutosh Maurya, can you answer solution? What is this strongest inductive invariant at location L2?
So 3 cannot be there because is the correction is there? So X can be equal to 3, or X can also be equal to 9.
Correct. Starting from 9, X can be 9. Then it counts down, so it stays there as long as X is greater than or equal to 3. So it includes every number from 9 till 3. But even when it is 3, it executes, and then it's only when it takes the value 2 does it execute. Yeah. So therefore, it has the same. It has every value between 2 and 9, inclusive of those things. Correct? Okay. And so that is the strongest invariant. Good. Okay. So as I said, yes, you can compute this strongest inductive invariant in general. By computing, I mean, given all these program, okay, I mean these transitions, conditional transitions, which are actually the program statements. I mean, I denote here as CFG. There is this whole logic gives you a way of mechanically, deriving this predicate, okay, as a formula in, say, in some logic, in first-order predicate logic. Now, in general, for all programs, that is undecidable because that will involve certain doing proofs in first-order predicate calculus, which is the decision problem there is not decidable. But you can, by making restrictions, you can either by restricting that, which means you have to restrict the class of programs, or you can use this technique of over approximation. That's where over approximation, under approximation, that concept comes in handy. Because when you do that, then this problem becomes not only decidable, but also more tractable. And that's why we are looking at this thing. And specifically in this course and in your project, you will be looking at how over and under approximations can be used to scale verification of DNN using these logical techniques. Yes, so that's that we will do, and that's why I'm spending so much time on this. Okay? So as I said, okay, I'll quickly go through this. I want to get to the interval domain. So for example, where if you only care about tracking whether the values that the possible values at these locations, either positive, negative, or zero, then you can actually map the actual set of values that the program variables can take into this kind of a domain. Okay, here in this case, it's a finite set of domains, and so then you could do that, compute these inductive invariants, the strongest possible, in this domain. Okay, which is called an abstract domain because it is an abstraction over the actual set of values. Here, the domain is the infinite set of integers, whereas here it's the finite set, which has these three elements that correspond to these predicates: x greater than 0, or x less than 0, or x is equal to 0. So when you take this abstraction, as you can see, obviously this, if you track this, it will, the actual values that this denotes, that, it may include all the possible values, but something more. But if all you care about is checking, if the property that you want to check and you care about is whether, about the sign, then this domain is good enough. Okay, that is the idea. Okay, so if you could derive the strongest inductive invariant in this domain, which with respect to the actual domain of integer values would be an over approximation. Okay, so that's why I'm saying, so if the initial value is that x can have is 2, then you can see that x can never be 0. Okay, I'm sorry, if it is, if with x is equal to 2, it is always positive. It can never be negative or the thing. So at each of these locations, L1 and L2, x always stays positive. Okay. Now, this is also an inductive invariant, but the inductive invariant, it's an over approximation of the original inductive invariant because it doesn't compute. It doesn't characterize the precise set of values, but a superset of the possible values that you can take. If the initial value is between 0 and 2, then at L1 it can become negative, and so it still will not be 0. Okay, so well, I'm sorry. If the initial value is between 0 and 2, then it can include 0 also. And I think there's a mistake here, because the first time you enter there, it will be 0. Then it will be everything minus or 0 or plus. Okay. If it is between 1 and 2, then also it is positive. Okay. And so on. Okay. And one can actually, computing inductive invariance in these kinds of domains, which are, abstract domains when compared to the actual domains, that is, which produce over approximations of the actual thing, as I said earlier, are much, complexity-wise, more tractable in computing. And there is a whole theory of computing inductive invariance in such abstract domains, and that area is called abstract interpretation, and tools based on abstract interpretation or static analysis as another thing. They are extremely popular in software industry, and they've also been used for DNN verification. And one of the tools that we will be exploring in this course will be computing these, doing verification by computing inductive invariance in such abstract domains. Okay, any questions there so far? Okay, so let me then move. Another very popular abstract domain that is used to track values and prove properties is interval domain. Okay, so for the same example, that is the thing. Suppose you wish to only track the largest and the least possible values that a program variable can take at a location in any of its executions. Okay, so you don't care about the actual values, but you only care whether it is anything between a lower bound, given a lower bound and an upper bound. Okay, which could be different for different locations. So these kinds of inductive invariance correspond to predicates which have this linear inequality shape. Okay, between with some lower bound and upper bound. Okay, so then you could then compute inductive invariance at each of these locations. For example, in this interval domain, what is the strongest thing that you could say about the values that X can take at location L1? Okay, so for example, you know that it can take between 2, 3, 5, or 9. So the smallest value is 2 and the largest value is 9. So an inductive, by saying that it can be anything between 2 and 9, it is still true at that location. Okay, because the possible values are actually included in that 2, 9. It is an over approximation in the sense that it permits values that are not possible in an actual program. Okay, but for example, if what you care to verify, if your property is a kind of overflow, underflow, that overflows and underflows don't take place at various locations, then this tracking computing inductive invariance in these abstract domains is good enough. Okay, and that's the thing. So now I question for who's next? Let me see. Debarshi, you want to take a crack?
Yes, sir.
Okay.
Okay.
Yeah, my question is, what is the strongest in interval domain, its strongest invariant, inductive invariant at location L2? What, in a sense, I'm asking, what is the smallest and the largest value that X can take at L2?
Smallest will be like, it should be greater than 3, so it should start from 4, right? And it's greater than, so long as it is, so long as it is greater than 3, it remains there. So the moment it is more than 3, it will go away.
No, that's not true, because it actually enters when it is greater than or equal to 9 and stays there as long as it is greater than or equal to 3. Okay.
Yeah.
And it actually stays there when it is 2, because this actually gets checked, the termination, the exit condition.
Okay.
So it's actually 2 and 9. There also it is 2 and 9. Okay. So that's how. So you'll have to do that kind of an analysis. Okay, for all possible values based on the conditions, entry conditions, and the other thing. So yeah, so the answer is, it is between 2 and 9. Okay, how about if the initial value, if you allow it to be between 1 and 2? Okay, I want to go next. Dribajoti. He dropped off at the right moment. So I'll go Nabin. Nabin, Sahu?
Nabeen.
Nabin, okay.
Yep.
Yeah, I want what the strongest thing that you could say in the interval domain, strongest inductive domain, L2, if it is between, if I allow the initial value to be anything between 1 and 2.
Okay, so if x is 2, then like it would be same as above. And
If it's between 2 and 9,
If-
if it is 2, yeah, if it is 2, I mean, sorry, if it is 2, we already know that it can be between 2 and 9. What happens when its value is 1? If the initial value is 1,
1.
if the initial value is 1, it kind of circulates here. X takes 2x minus 1,
yeah.
which is 2 minus 1, 1. It remains 1, okay? So it pretty much gets stuck in location at 1, okay? Correct. So it enters location L2 only if the initial value happens to be 2, okay? So therefore, it's still is between 2 and 9, because if the initial value is 1, it doesn't add any value to L2 because it doesn't get there at all, okay? So yeah, so it is still between 2 and 9. What happens if my initial value is exactly 1, precisely 1? Then this program gets stuck in location L1 and never even enters L2, okay? So because it never enters L2, the set of values that it takes is empty, okay? So really the strongest inductive invariant there is just strongest inductive invariant which corresponds to empty set of values actually false, okay? And so inductive invariant can be true, in which case it is true at a location if it can take any possible values in the domain of values. Okay, those are two extremes. So in this case, between 1 and 2, the possible values that if ever control reaches L2 will remain to be 2 and 9, because if the initial value is 1, the control never reaches L2, and that's why it doesn't contribute. So that's how you do. And once again, I want to make the point that these kinds of, there are several abstract domains for which this problem is decidable and quite tractable, okay? And one such domain is what is called polyhedral domain, okay? Where instead of interval, you have this general set of values expressed as a conjunction of linear inequalities, okay? And that's what is called a polyhedral domain or template polyhedral. You have a bunch, a conjunction of constraints, okay? That kind of a domain is extremely useful when we, and these kinds of invariants can be computed, okay, in those cases as well. And with DNN, polyhedral domains or even interval domain might be useful, but if you want to precisely compute, because mostly it is linear combinations, I mean linear arithmetic is used, polyhedral domain over approximations based on polyhedral domains will be quite useful, okay, in the okay, so in the context of okay, I'm already 5:30. Okay, let's see if Diganta is here. they're still not here, so I can continue. I will continue since I have not finished my making all the observations that I want to make. Okay, so the reason for similarity between these two things, you see, a feed-forward neural network, when you look at it as a program, it is a straight line program, correct? It does not, in the sense, it does not have any loops. Therefore, so the computation at each of these nodes after the ReLU can be expressed as a composition of the linear transform that happens on the input to that layer, followed by the activation function, which in this case happens to be ReLU. Okay, so each layer, the computation performed by a feed-forward neural network can be expressed as a simple assignment to the whole bunch of variables denoting the values produced at these nodes, the output of the activation functions, and they can be expressed as simple assignment statements. And therefore, you could compute this by computing the strongest inductive invariance. At the output of each layer, you will be capturing the set of all possible values that that can ever occur at those nodes for all possible inputs, and then you can keep doing that for each layer, and the strongest invariant that you get, it may be an over approximation, but that you get at the output layer can then be used, okay, because that includes the set of all possible values, that can actually use that to check your whether any value in that set violates your post condition, your condition that expected condition. That is why, okay, I hope you understand. So the techniques for computing the strong inductive invariance are relevant in that sense, because they capture you can do the same thing for DNN. So by computing the set of all possible values as inductive invariance at each layer, then you have captured all possible values, and therefore you're able to use that. You can rely on these program verification techniques to verify your property, and that's what we will be doing. Once again, precisely computing these as precise predicates, which exactly characterize the set of all values precisely, is going to be computationally hard, and that is when we use over approximations. Okay, and that is the relevance for learning about over and under approximation. Okay, any questions here? Okay. Yeah, later in the course, we will what we've shown here through tools, we will see how DNN can be verified. But I just wanted to make that point here, and I hope I have made that. So let me go back into this. By the way, there is a dual of this concept, of over approximating the set of all possible values at each, location or at each layer, as the case may be in the case of DNN, which is an under approximation. Okay? And that sometimes you might wonder why. Okay, what is an under approximation? An under approximation of an actual invariant at a location is a predicate characterizing a set of values that contains only a subset of all values that where you take at that location in any execution of a program. A predicate at a location that includes values up to and including only 2 iterations of all loops, if any, that are headed, that have their heads at that location. Okay, if indeed you're tracking or computing that as the set of all possible values that can ever occur in loop iterations up to 2. Okay, that is an under approximation. Okay, so if you want to verify certain properties don't get violated, only up to certain bounded iterations of the loops, that could be one possible reason to consider under approximation. So it is it is useful to use under approximation as well, because even if with this under approximation, if your property gets violated, because an under approximation is still a legal behavior of your program. So if with an under approximation, if your property gets violated, then you've found an error. Okay, so that's why having under approximation to show presence of errors is still useful as a verification technique. Okay, so for example, an under approximation of the strongest inductive invariant that you can compute in the concrete domain is after 2 iterations, for example, up to 2 iterations, x equal to 2, 3, and 5. Okay, and similarly at location L2, it'll be what is it that it actually, this is wrong. Okay, it will be, this is wrong. Okay, so I will, can anybody guess what the thing? I say that this is wrong. I made a mistake here. What is it? Maybe not. Yeah, it's a mistake. Can the next person in the thing, Rohan Dharmadhikari?
Yes, sir.
Can you take a crack?
Yeah, just give me one second.
This is a bit of a trick, okay? It's a tricky question, so maybe I will answer it. So if you only consider up to 2 iterations, will it ever exit L2, L1? See, with initial value x is equal to 2.
Yeah, and as long as it's less than 9, it will still stay in L1.
Still stay there. So this is kind of a bad example for that. So, but it's interesting in one way, since it if you look at only under approximations up to 2, the set of values at L2 will be empty because the control never gets there. Okay, it's only after it gets there that it that it can even do some computation there. So that's, in that sense, this is wrong. Okay, so yeah, you get the idea. Okay, so and we will later on discuss in the context of DNN how certain techniques exploit these concepts of over and under approximation to scale verification. Okay, so let me see if Diganta is still not here. So I will continue with this discussion. So I want to show a few slides from the person who's credited with inventing this technique of computing strongest inductive invariance in abstract domain in a particular fashion, developing the theory and the techniques and the tools. It's a husband and wife pair. I'm going to use some of the slides from one of the that husband and wife name is Kuzo, Patrick and Radia. Radia is no more. His wife passed away, and they are credited with inventing abstract interpretation, which is the one popular technique, not the only one, for computing, doing inductive invariance in these abstract domains such as intervals, sines, and polyhedral, and so on. Until Diganta gets here, so I will upload this thing as well. Okay. So here is a kind of I'm going to only show you some selective slides from this person because they are very intuitively they capture what's happening and how these over and under approximations are being used. Okay, so given a program, there's a bunch of locations. So that's the notion of time that is have. So the behavior of a program can be captured by a trace, okay, which gives the value that the program variable takes at each of those locations. Okay, so going from one location to another location, you execute some instruction. Okay, it's in that concept. So that is a program behavior is a set of traces, and that's what inductive invariants are capturing anyway. These traces are being captured because we associate an inductive invariant which characterizes the set of all possible values that the variables can take at that location. So for each of xt, these values, the set of all possible values, are characterized by the inductive invariants. Okay, so when you have some safety property, okay, saying that some conditions shall not be violated at a particular layer or output layer in a DNN. Okay, so with respect to DNN, each layer, if it has 10 layers, then T will be 0 through 10. Okay, whereas if it's a loop, then this trace can be arbitrarily long. By the way, there is this class of neural network, a variant called a recurrent neural network, which can support loops. Okay, and those loops mostly are bounded loops, but they could be unbounded loops also, in which case this way of characterizing the behavior of that neural network by characterizing the set of all possible values that it can take after every layer is very much relevant. Okay. Okay, I think Diganta is here. Diganta is here. Okay, so I will after I show this, I will pass the baton to Diganta. So Diganta, just hang on for a few minutes. Yeah. Yeah. So the areas that the violation areas, these are shown in red here. So a program, if you consider all possible, a verification technique usually, you cannot enumerate all possible values because that can be infinite. Therefore, it really computes these as symbolically as inductive invariants, as formulas, and that's why you can talk about set of values. So a safe program is one in which every value on this trace never intersects with these forbidden areas. That is what is the thing. So by computing these symbolically, these traces, which in our case, I was illustrating the use of inductive invariance at each location, you will be able to verify. Okay, that is the concept. Now, in the case of testing or simulation, what you do is, simulation enumerates each of these traces. Okay, and then checks if at any point this the value of x gets into the forbidden zone. Okay, but of course that is not exhaustive. You can't do exhaustive simulation. That's why it is not a complete proof of verification. What we are aiming through these logical techniques is to verify the given properties that the expected behavior is never violated for all possible inputs. Okay. That a neural network, for example, can never take. So in terms of when you do it symbolically using, for example, as inductive invariance, this is what you're doing. You still have the forbidden zones, the red zones characterized as properties, okay, which is what I illustrated in the case of DNN modeling. And what you do is by computing inductive invariance, maybe an over approximation of it, as an over approximation at each location in a program or at each layer for DNN. This is what you're doing. It is the green area that you compute, okay, which you see in this case is an over approximation, okay. Why so? Let me ask the next person after Rohan. It is Soham. Soham, why is this green area an over approximation? Are you there?
Yeah.
How did it define over approximation? It should include all possible values that the program can ever take, all possible behaviors, in this case, the traces, but something more. And you see, these lines are the actual traces, all the possible trajectories that the program can go through. But as you can see, this has more of them. It includes all of them, okay? And that's why this is an over approximation. And that's what you do when you compute it in using abstract domains such as intervals, a polyhedral domain, and so on, okay? And the answer that I was expecting from Soham was that the reason it's an over approximation is because it includes all possible trajectories that are ever possible for all inputs of that program or DNN. Okay, as I said, in the case of DNN, the T ranges over the layers. Okay. Yeah. So the green area. So this is kind of the the most abstract abstraction that you can do. So the most abstract abstraction that can still work for verifying that this program is safe is this green area, which can extend all the way, but not go into the forbidden zone, okay? As long as your over approximation does not excludes this red zones, it is still can be useful for you to verify that it is safe, okay? Now, for example, here, your abstraction is not an over approximation. Why? Because you see at this point it does not. The green area excludes some real possible value. See here, the one where I'm moving the cursor. Okay. So if you want to prove that a program is safe, that it never gets violated, it is okay to use an over approximation as long as it includes all possible behaviors, okay? Even with an over approximation, if your property does not get violated, then you know that it is still safe, okay? But it's very important that it must include, it must be an over approximation. Yeah. Yes, Niganta. Yes.
Yeah, hi, so sorry for being late.
Yeah. So that's what. So that is why when you devise a method for doing it, you better be sure that what you compute those inductive invariants are the true over approximation in each of the layers. Okay, for a neural network. Okay. Now, for example. So I also introduced to you in a slide earlier the notion of an under approximation. Okay, so with respect to program, I said that if you only consider loops up to a certain point, for example, this green area is an under approximation because it still excludes all the behaviors to the right. Okay, therefore an under approximation is not good to because it can still using an under approximation, you cannot give a complete verification. But as I pointed out, it is still useful to check if even with an under approximation, even with this under approximation, for example, if the dark green area overlapped with the forbidden zone up there, then you could say that you can find an error. Okay, so it's a good effective technique to debug to show maybe possible presence of errors. So, that's why we will also use, one can use under approximations as well. Now, there's another thing that can happen, okay, when you use only over approximation to do, okay, to verify things. Now, your over approximation, this is a truly over approximation. The green area here still includes all the possible behaviors. So as per our definition, it is still an over approximation, okay? But it is too coarse, okay? In the sense that it includes certain behaviors which happen to, which are not possible, which are not legally possible behavior of a program, but ends up violating the property that you're trying to prove. In that case, such a coarse over approximation, if you use, it can give you false alarms, okay? That is an occupational hazard of a verification technique that uses too coarse an over approximation. So, you are taking a bet, okay? So, because this can be false alarms, so they might still be useful. I mean, if it gives that it is safe, then you can be sure that it is safe, okay? With an over approximation. But if it fails, then you can't exactly, without further analysis, you can't tell if it is a true error, a true bug, or a spurious bug. And that you can only check by getting the counterexample and then actually simulating it. That is one way to find out. Simulating it on an actual neural network to see if it is a possible error. So that is, a drawback of using over approximations. Okay, and this is what is over approximations can, when we say it trades precision, that is it introduced imprecision. This is what is meant, that it can be too coarse, okay, for a particular kind of property, in which case you will have to refine your abstraction to remove, to make it less coarse and less imprecise, okay? These are also, techniques that we will look at in the context of verifying neural network with over approximated. This is all I had to discuss and take questions. It is 5:53. And, so we can go till 6:15. So Diganta will have some time to introduce the ACAS network. So I'll take any questions you might have, okay? Any questions? No questions. Okay, you can always ask questions after, if it comes up later in your future classes as well, or anytime. So if you have no questions, then I will hand over, stop my sharing, hand over we can co-host, and now you can share and take it away, Diganta.
So I'll just start screen sharing.
Yeah, you can go to 6:20, okay, because people take 5 minutes. I think I'm going to use one general thing, and I think I'm going to wait till 5:05 or until I get a quorum, okay, of the class, and I'm going to start. If that happens, whichever happens earlier. So I will start, and I'll only wait till 5:05 p.m. And if I go till 5:05 p.m., then I'll, without any guilt, I will go 5 minutes late, okay? That is the general rule that I'll follow. Okay, go ahead. Yeah.
Yeah, okay. So basically I'm going to talk briefly about this ACAS-XU DNN system. So in general, this is actually some DNN that has been developed to tackle the collision avoidance problem. And the way I'm going to basically talk about it is in two parts. Firstly, I'm going to describe some brief history of the collision avoidance problem, how it is used in the aviation industry, just to give you a perspective of the industrial significance of this system if it gets certified. And then I'll talk about, what the neural networks are, what inputs they take, what outputs they take, what does their structure, how have they been trained, and so on, right? Okay, so this is just some motivation regarding the need for actually, automatic systems to detect collision between aircrafts, right? So the thing is, like, there is a lot of aviation traffic nowadays. Like, if you ever live near an airport, you're going to hear a plane every 2 or 3 minutes, right? And the issue with aircraft is that, like, they're really fast, they're really hard to spot if they're far away, and they approach each other very quickly. And even if they don't collide with each other, if aircrafts even get within like 1 kilometer of each other, the turbulence caused by one plane can actually lead to a loss of control in another. So they have to maintain a good amount of separation at all of the times, right? And, you can imagine the situation where, say, you have two aircrafts, both of them are traveling at 500 or 600 kilometers an hour, which is a huge speed. And they're both approaching each other, right? So they're like, if you're on one aircraft, the other aircraft is approaching you almost at 1,000 kilometers or 1,200 kilometers per hour, right? And then visibility might be poor. So maybe you're at the moment in a cloud, then you can't even see the other aircraft. Like, if it's approaching head on, you've got nothing to do, right? And even if you can, like, if the visibility is good, it will still be too hard to, actually spot the aircraft. And even if you can spot it, how would you be able to tell? It's like it will be some speck in the distance. You can't really tell if it's approaching you, how far it is, which way it is going, and so on. And since the speeds is so high, even if they spotted, you will have like only maybe 10-20 seconds to react. And you can imagine it takes a lot of planning and careful effort to move these aircrafts away from each other in a safe way, right? So we really can't rely on pilots alone for collision avoidance. There are some situations even in modern aviation where this is still the case, but with commercial aviations, we no longer ever rely only on pilots for collision avoidance. This has not been the case since World War II, right? So we need some sort of external agency that will take this load of checking for collision avoidance off of pilots. So of course, the first thing that people tried was actually use ground-based traffic controllers. And we still do use them, but we don't use them exclusively anymore. So the ground-based traffic controllers, their job is sort of they have this radar screen, and on the radar screen, they can see the position of all of these aircrafts. And their job is to monitor this entire screen and check whether any two aircrafts are in such a path that they're going to collide after some time, right? And then if those two aircrafts are going to collide, they're going to radio these, the pilots of the aircraft and ask them to move in a way so that they no longer are on a collision course. So this is, it sounds good in theory, but of course, in practice, there are several issues. One is that, of course, there's large amounts, even today, there's large amounts of uncontrolled airspaces, right? Which means that there are these regions of the sky where actually no ground controller is able to get a radar lock over there, right? So nobody's really controlling the traffic in those regions. It's hard to get like complete coverage of the sky, especially over the ocean, where you can't even have like a ground radar station or something with it, right? The other issue is that often ground controllers don't have complete or up-to-date information, right? So oftentimes what they'll do is if they don't have the radar equipment, they'll sort of use or ask the pilots what position information they have, and then maybe every 5 minutes they'll update that position information. Of course, that is like a very high latency situation, right? And that is, not even enough information to guarantee any kind of safety. And then, this is all dependent on communication between pilot and ground. And there have been actually very serious, multiple very serious accidents where the sole or the, let's say the critical cause was lack of or breakdown of communication between the ground controller and the pilots on the ground. In fact, the worst air accident in history till date happened because pilots misinterpreted the communication that they were receiving from the ground controller. And even if communication is perfect, it's all humans and there is human error involved. So if you would want to, you can read up on this particular aircraft collision, which was for a long time, it remained the worst air collision or even the worst air accident in general. And it is a very grim sort of a situation. And this situation has been repeated several times where this entire synergy between ground controllers and pilots completely breaks down, right? So because of all of this, in 1981, the FAA in the USA, they sort of started to look into developing this ground independent system to alert and provide some sort of advisories to avoid collision, right? And the idea is that you will have this system on the aircraft. There will be no ground controllers involved, and the system will automatically sort of tell the pilot that, okay, you're going to collide, you should do this, right? And the system that they developed in 1981, or they started developing in 1981, it took, I think, around 10 years to develop and deploy completely, was called this Traffic Collision Avoidance Systems. It's got a short form, it's called TCAS. And if anyone is sort of an aviation enthusiast, they'll know that this system is actually very widely used right now. Like all commercial aircrafts have to have this sort of a system. It has to be operational for them to legally fly. You cannot nowadays fly without a traffic collision avoidance system installed on your plane. So this system was basically, the development was announced, or the beginning of development was announced in 1981 by FAA. And it's based on some simple logical rules, right? So it's not a very complicated system. It's based on some simple logical rules. Rules like, okay, if the plane is approaching at this speed from this situation, then the guidance of the advisory should be this, right? And these rules were sort of written by experts and validated also by experts. So it's just, since a list of rules, there's not much. Like, it's not very hard to validate it from the perspective that we think about validation or verification, but the rules themselves have to be sound. So that was actually validated by domain experts, pilots and aviation experts, and these sort of people. They wrote down and cross-checked and validated that the rules are good. So the way this system works,
I want to interject here. Okay, just a certain historical. I think there were, if not, okay, I think there was a person called Nancy Levison. Okay, she became very famous when she used Boolean satisfiability much later. I think, if I'm not mistaken, it is TCAS to verify Leveson, Leveson.
Okay.
One can check and see if my claim is correct or not.
I'll just maybe look at that.
Yeah, actually, she probably did not. I mean, she used something like decision trees to analyze these TCAS. Okay, that was kind of the first attempt at using some thing like formal methods towards ensuring that the rules that were modeled in TCAS did not have any inconsistencies. Okay, or some.
I see. Okay, that is very interesting. I'll take a look at that.
Yeah. Go ahead.
Yeah. Yeah, so I mean, all of this I'm saying is some history that
Right, it's useful. Yeah, I think.
So right. So all of this is, by the way, like, this is introduced in 1981. So I think this Nancy Levison, when did she do this, sir?
I think it is, I would say,
like in the 90s, late 80s,
late 80s and early 90s. Okay,
right.
That was the time that it got a lot of attention. Okay, when SAT solvers were still in their infancy. Okay, I mean 2001 is when SAT solvers just exploded and came into the horizon. I mean, into the note of all. It was prior to that, but that's why I said that it was not exactly a full form of it, but then kind of a semi-formal way of analyzing, more systematic.
So one of the things that I could actually look at was, like, when FAA announced and was sort of developing this, I guess from FAA's perspective, it makes sense that they are talking about validating by, like, people who are actually experts in the aviation domain, because they'll have some sort of domain knowledge about how safe it is of a distance do we need in terms of separation.
I mean, domain experts are needed. Okay, no amount of logical verification can completely validate in the true sense. Yeah.
So, okay, so, right. So, I mean, okay, so I'll just talk a little bit about the way these things worked in terms of like the machinery, if you will. So the way it works is that aircrafts have these things called transponders, which are like radar units, which communicate both with the ground radar if one is available and in range, and with any other aircraft that might also be in range, right? And the transponder will sort of give out information like, okay, this is me, this is the identification of the aircraft, and here is where I am, and here is where I'm headed with this much speed, right? So since we have these transponders, they will sort of, they can be used as a communication tool between aircraft. So whenever an aircraft receives a transponder message from another aircraft, it will actually use these rules to check whether there is a collision that is going to happen, right? And if it is going to find that there is going to be a collision, this is going to provide an advisory. So an advisory will be some sort of an alert or a message the cockpit, some screen the cockpit will show to the pilot. And this advisory, in the case of TCAS, it's usually going to say something about climbing or descending. So the advisories are going to be like, okay, you have a collision, you should climb faster, or you should descend and you should descend faster, and so on, right? And it doesn't, give you advisories about turn left or turn right. It's only a vertical sort of advisory that it gives. And another interesting fact about the system is it will actually provide complementary advisories to both aircrafts, in the sense that if one aircraft is being asked to climb, so if say you have a situation where two aircrafts are approaching like this, if you ask one aircraft to climb, if the system asks one aircraft to climb, then the system will definitely ask the other aircraft to descend. And this is actually guaranteed within the system, and you won't have a situation where you end up asking both aircrafts to climb and you still have a collision course, right? So this system actually already exists, and as I was saying, this is like validated and deployed, and this is being used in all commercial aircraft right now. But even this system has some issues, which is why the FAA is looking into some new systems now. And those issues pertain to mainly unmanned aircrafts. So there are various domain-specific reasons why this TCAS system is not suitable for unmanned aircraft. One of those reasons is, or some few reasons are, that this TCAS system actually is a human-in-the-loop sort of a system. It still requires human decision-making. Like there are some situations in which the TCAS system is going to sort of tell you that, okay, there is a collision, but it's not going to, ask the pilots or give the pilots direction or specific directions on what to do to avoid the collision. So in this sort of situation, the TCAS system says that, okay, I'm not smart enough to figure out what you should do to avoid the collision. And then the pilots, the crew is expected to resolve the situation using radio communication between the aircraft, right? And of course, this is not an option at all for unmanned aircraft, right? If you have a drone, then, you can't do that at all. And of course, this TCAS system, since it's asked, when it gives you a direction, it asks you to climb or descend. This will actually not work when climbing or descending is not an option. So, for example, a lot of drones will actually fly fairly close to the ground, say only 500 or 1,000 feet above the ground, right? That might seem like a lot of space, but for a drone that is traveling very fast, or even for something like a commercial aircraft, definitely is like no space at all. But even for drones, it doesn't really give you too much room to descend rapidly to avoid a collision, right? Similarly, drones may not be actually powerful enough to also climb rapidly to avoid enough separation to, say that you have avoided a collision. What they might be able to do more effectively is to turn. So we would want something that, gives you both turning and climbing sort of advisories to avoid a collision, right? So because of all of this, recently, this sort of a system is being looked into, which is called the ACAS-XU, right? And the features of this, or the important features of this, is that it's going to be human independent, and it's going to produce both horizontal and vertical advisories. So I'll go into the details of what the ACAS-XU system is, what the exact inputs are, what the advisories are, because we sort of need to know that to understand what the networks are and what the properties are. But for now, just for this slide, this is going to just be some system that looks at the data and gives you some advisories that's going to be like turn left or climb or do something like that, right? So this is basically the ACAS-XU system. What I want to talk about at this point, so this was sort of the historical idea here, and now I'm going to go into a little bit of the details of the ACAS-XU system. So is there any doubts or any comments or anything about the history? Okay, sure. So I'll just go into the details of what this ACAS-XU system is, right? Usually the first time when people produce or propose this ACAS-XU system, they did not propose it as a DNN. In fact, the version that is being certified by the FAA is not a DNN. That version is actually based on a large lookup table, right? Which means that you're just going to have this 2 GB worth of tables where each sort of cell in this table is going to be something like is going to be indexed by all of the inputs, right? So for example, if your inputs are your position and velocity of the aircraft, so involved in the situation, for example, then you're going to sort of you have your table be indexed by ranges of position and velocity. So you're going to say that, okay, for this cell, the range of the position is between, say, 1,000 and 1,050 feet, right? And you can say that the velocity may be something like 20 and 21 feet per second, right? So maybe for this particular, if your situation lies within this particular ranges, then you're going to go into this particular cell and look at whatever advisory is there in that cell and produce that as the output of the system, right? So it's just a huge table which just categorizes what to do in each sort of situation. And of course, things are continuous valued. So you can't really sort of say that, you can't really say that what to do in each particular value of the input, but you can say what to do if your values are within this range. So if your speed is between this range and your position or distance is between this range, then do such and such things, right? So this is how the sort of, how the system sort of works. So the way they actually created this lookup table is by using or modeling this sort of collision avoidance problem as a Markov decision process. So if you don't know what an MDP is, it's not really going to be very relevant, but I just wanted to say this as for people who do know and are curious. So they model this collision decision process as a Markov decision process. So that's basically they're going to sort of allow the craft to make decisions and then simulate what's going to happen, allow the craft to make more decisions, simulate what's going to happen, and keep on doing these steps. And finally, if a collision occurs, then they'll give a huge penalty, some huge penalty they'll give. And if a collision does not occur, then they'll give some huge reward, right? And so this gives you some, this final thing, the penalty or reward that you get, you can sort of estimate the expected penalty or reward that you get. So you can do an expectation over this and then sort of maximize that, right? So if you model this thing as an MTP, then you can sort of propose this or pose this sort of finding the lookup table as a maximization problem. And this maximization problem was solved via dynamic programming. So nowadays we have very sort of sophisticated machinery for reinforcement learning and all of this, but what they used was dynamic programming. And I think this was sometime in 2012, if I'm not mistaken. So they use dynamic programming to sort of solve or exactly maximize this MDP. And you can do that. If your MDP is bounded, you can actually show that there are some dynamic programming algorithms where you can find the precise maximum, which is unlike other DNN or machine learning algorithms. That sort of a guarantee is not there in other fields. But they sort of gave that, and they found sort of a best possible table for various parameters by dynamic programming. And this table has been certified by the FAA. So the FAA is being certified. So the FAA is actually in the process of slowly certifying this and creating a standard so that now they'll create this category of unmanned aircrafts which will have to have something like the ACAS-XU system. So this is the classical ACAS-XU system, if you will. What we are more interested in is a DNN-based ACAS-XU system. So in 2016, there was a paper by Julian and others, and this is the sort of the name of the paper is in this bullet. So this paper, they looked at compressing this lookup table because 2 GB, even in 2012, definitely 2 GB is a huge amount of memory to have, right? And in 2016 also, it's a huge amount of memory. And if you think about drones, they don't have very powerful systems in them, right? They're designed to be low power, efficient, hardy systems, not powerful systems, right? So for them, 2 GB is a huge memory footprint. So they looked at if you can compress the table somehow. And one of the ways that they explored of compressing this table was using DNNs. So what they did was that they took a DNN and then they trained it on the table, right? So the table itself is just a bunch of input and output values, right? So you can think of the entire table as being this huge data set, and you can train a DNN on that. And what they found in this particular paper is that, one, they can reduce the memory footprint hugely, which is not a surprise because, after all, the DNN would be much more compact. In fact, they reduced it to a few megabytes, which is a huge amount of reduction. And secondly, they found that if under simulations, the DNNs were performing almost as good as the table itself, right? So the DNNs are actually, performing very well. And because the DNNs are by their design continuous, they're actually sort of smoother. They don't give very, there's no rigid boundary in which the advisor suddenly switches, which is what the case with the table sort of a situation, right? So the DNN based compression is actually smoother, and it seems, if you simulate it, if you sort of run many tests on it, that it seems to perform as well as the table, right? But of course, now this begs this natural question that does it actually perform as good, right? Is it actually safe? So these DNNs, this ACAS-XU DNNs is what has emerged as sort of a natural standard benchmark for safety analysis of neural networks, right? So various algorithms sort of target this as a safety analysis target because, of course, if you can come up or if you can show that this DNN is actually safe, then that allows you to deploy this DNN, and that will, allow you to actually deploy DNNs in general in these other fields where they can lead to huge computational benefits. But people can't do that for lack of certified safety.
Yeah,
right?
Diganta, you have 5 minutes. Hard stop at 6:20.
Yeah. So I think maybe I can even stop here because the rest of the details, I think I'll.
Yeah, but I had one question. I know
Right.
that you mentioned, go back, that it is benchmark for safety analysis. Just that, or is this ACAS-XU is actually deployed and being used?
Right. So I'll say that. So basically, there is 2 versions, like I said. Then one is the lookup table version, right?
Yeah,
that's
what I know. Yeah.
Right. So the lookup table is being certified. It's not yet deployed, but I think they're like looking into deploying it soon. The FAA is sort of moved slow with all of these things, from what I at least gathered. But this DNN is actually not deployed anywhere yet. People are, or at least the FAA is not convinced about the safety. And I think there was this one paper last in sort of this one, right, where the NFM, where they showed that under certain sort of conditions in closed loop analysis, it turns out that these DNNs can produce collisions in some situations, right?
Yeah. I remember that. So by the way,
Yeah.
for people who are not familiar, NFM is a kind of is one of a conference, okay, called NASA Formal Methods Conference. Okay, so it brings together people from this area of formal verification, and there is a lot of interest there now for verifying machine learning and DNN. And these safety critical companies and institutes, which includes NASA and so on. So that's a conference that is focuses on that. Okay, I do remember. So there was a paper there saying that it is basically there are some scenarios where it is really not safe. Correct.
Yeah. And whether that is good enough for FAA or not is something that I don't know. Yeah, because those scenarios were sort of scenarios or particular scenarios, right? The FAA usually doesn't, from what I understand, like even with previous systems, they don't ever expect like foolproof safety, but they want some margins. So and they want to verify those margins. So it's not clear whether this will get deployed, but so this is not deployed as of now, and so it's not close to being deployed.
Yeah. Okay. So 6:19. Okay, just 1 minute.
Right.
So anybody have any questions? So maybe this is a good place to stop rather than get into details. Yeah, which you will do. By the way, Thursday, is Thursday okay with everyone? I mean, I'll send an email. Okay. So Thursday you have the regular time is what, at 6:30?
Yeah, 6:30. Is that okay with everyone for tutorial? So I'm basically probably going to continue
It's not
this.
exactly a tutorial. I mean, it's a regular
Yeah,
lecture.
yeah.
It's a
Yeah, this
makeup
time
class.
it'll at least be a regular lecture.
Yeah,
And
So
if
can
not-
we have this lecture at 5 p.m.?
Thursday?
Yeah, tomorrow, right? So
Yeah, tomorrow
I
5.
have a
6:30
lecture at 5 p.m. tomorrow.
Oh, okay.
Yes, I remember somebody saying that they had a lecture on Friday. That's why. We can do it later than 6:30 if that is better for you.
So then I want to be, I mean, later than 6:30.
6:30 is it wasn't.
It was not convenient anyways, that right, what you're saying, because it intrudes into your meal time. Huh? Is that the issue? If I make it compulsory? I mean, you guys have to answer. I mean, you just ask a question and you don't answer.
I think the person has dropped off probably.
Yeah, okay.
Because
it's fine, I think. One could not say, but it's fine.
Yeah?
6:30.
Okay.
About
It's
Okay.
6:30. Okay, I guess we'll just take that.
Yeah, so I'll send an email. And if there is vehement opposition, then we'll have to look at something else. Yeah, okay.
So
For now, tentatively 6:30 on Thursday. Yeah.
yeah, so if anybody has any issue because of which you can't attend at all, then do let us know, right? Because this I think might be a little bit important for the project because
yes, it's important for the project that you need to understand, and you will get an opportunity to experiment with it and so on, but you still need to know.
yeah, and I'll show you what the network is, what the structure is, where you can download the networks and so all of that. So
Okay, so no questions, then I'll stop.